All right, welcome back. I thought today I'll kind of maybe wrap this up a little bit and then look at a few other aspects of performance of memory access, both in terms of what the compiler can do and in terms of what the processor does, what speeds things up, what slows things down. First, I thought I'd mention a little bit about the midterm, which I forgot the date now. It's not next week, but the Tuesday after, I believe. What was that?
The 16th?
Yes. The 16th, yeah, that's right. So if you haven't had a midterm with me in the past, if you've taken 361 or 385, I think you know what the deal is. But basically, there will be relatively few conceptual questions. There might be one or two. Most of them will be quite practical. So you might be faced with a problem, a concrete problem of, here's a piece of program that runs slow. Either maybe we might see some profiler output about it, maybe not. And then it'll be your task to either diagnose why it might run slow or propose a simple fix, that sort of thing. So sometimes, it could be that we want to know, just understand why is it running slow. It can't be fixed, right? But it's just running. It takes this long because of this or that. Or in many other cases, a simple change to the program could make it go a lot faster. So, so I think generally speaking, it'll be problems like that. We can't have computers at the exam, unfortunately. It'd make it really awkward. Otherwise, I would really prefer that we had, we're doing a whole bunch of little programming tests, right? But that I just don't know how to do that. Like, people should have internet connection. When you're programming, you should have an internet connection. And at the same time, when you're taking an exam, you definitely shouldn't. So I don't know. So we'll just have to make do with paper. Right, any questions on the exam? Generally speaking, they tend to be hard. Don't worry about it, do your best. All right, so I stopped last time. We were talking about this mFence, and I think I figured it out. So, the part that I was a little confused about is how Intel implements this mFence, and it's probably not so important to us. What we need to know is that this mFence instruction prevents any reads from happening earlier than it looks like. Like, they can't travel across an mFence upward or earlier in time. But the impact of that is essentially that they can't read old cache values. Right? That's the reason that reads can appear to happen before the writes. Let me get a little more concrete here. So reads before write. So if we have a move 1 to some memory address, and then we have a move another value to RAX. Now, this thing here in a multi-threaded program under the Intel guarantees, this instruction can actually execute before whatever was out of order and happened before the write. And so the challenge of that, or the reason that happens, is caching, essentially. It's also the store buffers, I suppose, but basically all this asynchrony. And so what is it that happens when you put an mFence in between? It's another x86 instruction. In that case, this move cannot execute before, which means it's not allowed to read a stale cache value. So how does that actually happen in the machine? That was the sort of the question where we ended. And I'll retract this statement that I think I said something about. I think you have to have a little delay. Probably that's not the case. So so imagine that we're running a move 1 to y on a different core and a move x to rax on that other core. Just as the example that we had last time. So basically this one, but we have an m-fence in between. So in this case, the m-fence prevents any further instructions, read instructions from running until the store buffer has been drained. Right? So this and these instructions here, the initial stores, they end up in the store buffer. It might take a while before the instructions retire from the store buffer. Or I should put that differently. The instructions retire as soon as the store enters the store buffer. But the actual store doesn't end up in memory, and it doesn't leave the store buffer until the relevant cache line has become exclusive mode on the core in question. So mfence waits for that to happen. Mfence waits for the store buffer to be empty before executing any further instructions. But that doesn't fix our cache problem, right? It doesn't say anything about clearing the cache. So that's sort of where we ended last time. And what confused me about that is, well, basically, what do we do about these cache lines? So the answer, I believe, is that this stuff only works if we put an mfence on both sides. That's the only case where you'd get like a nice consistent output. So by the time the store has left the store buffer, then we are guaranteed that there are no stale values in the rest of the system for this, in this case, for the X. So by the time the mfence has finished, we know that there is no old X anywhere in the system. And that's when we go read our Y. Same thing happens on the other side, right? We know that there are no old Ys in the system anywhere. Only after that do we read our X's. So the only way that we can know that there are no old values in the system is that the core, when it was trying to do this right, it's in the store buffer. Store buffer asks all the other cores, like, do you have any copies of this thing? If you do, get rid of them. Right? If they are just read-only copies, which in this case they would be, we don't have to get their copy. We don't need to know what their value was. We just need to make sure they don't have it anymore. So we send a cache invalidation message that goes over the memory bus. And that's not enough. We don't know yet that they've actually removed it, so we're not safe. We have to wait to get an acknowledgement. So there's going to be a message going out saying invalidated, a message going back saying, yeah, okay, I'm done. I don't have this stale value anymore. You can continue executing. And that's what happens with the mfence. Okay. So I had a whole bunch of other experiments that I thought we'd play around with. We'll start with a few more performance things. So last time we weren't really doing performance. We were looking at consistency when we're doing this concurrent access to memory. So I thought we'll try to see what happens with performance when we're doing the same thing. We've seen a little bit of this fault sharing. That was an interesting experiment, I thought, but we can take it a lot further than that, I believe. So let's try a few different things and maybe try to understand what the machine is up to. Okay, so here's a version of the code that we used last time. It's just kind of, I cleaned it up a little bit. We have, in this case, we don't have all these barriers, right? The barriers were there in order to make sure we had the two threads executing their one single assignment at the same time, or as close as possible. In this case, we just want to have them go fast. So now I'm starting two threads, and then I'm telling both of these threads to get going. So in this case, Actually, I don't think we can probably do without that one, but that's okay. So the two threads are waiting on a barrier before they start writing, and then they do 100 million iterations of some work. So I think we had something quite similar to this a couple of lectures ago. This was the two increments sort of code. So let's just start with that. Go to, oop. Okay. Oh, and by the way, if you've not set it up like this, if you're doing it in SSHing, if you don't have your machine set up this way yet, do it. Right? So I'm not typing in a lot of passwords. I'm not saying my username, anything like that. Frames is a shortcut in etc hosts. Right? And then I guess you don't actually need that. You can set everything up in your SSH config like this. So you tell it what you want. Like for any given host, you can say which user you are and passwords you want to use and so on. Not passwords, but key files, presumably. And then there's the authorized keys. Oh. This one that says, oh yeah, by the way, if whoever's trying to log in has the matching private key, these are my public keys, so they're safe to show. But if whoever's trying to log in has the matching private key for this, then you're good, you don't need a password. Set it up. It's well worth your time. Okay. So let's try something. Sync perf. Oh. Come on. Let's get rid of that sound. Okay. All right. So same sort of program. I'm just printing out the pointers at the top there to make sure we have the alignment that we think we do. So here are, I didn't save this. Maybe now. Oh, actually. Huh. Actually, I don't understand how we, am I not saving the right value here? What's going on? It's aligned. X and Y should be. These are, oh, sorry, yeah, they are, is that 128? Yeah, it is. Okay, fine. Sorry. Yeah, so they're 128 byte aligned variables. Good. So they're on their own cache lines. All right, so we did this experiment before. It takes, to do 100 million increments, it takes us 300 milliseconds, but we're running it on 2 cores, the total execution time 600 milliseconds. All right, kill that. So if we instead use non-aligned variables, so they end up on the same cache line, just to reiterate, I'll just do it like that, just to see what it looks like. Okay, so that took a little bit longer, like 500 instead of 300. All right, not so bad. So I wanted to look at what happens if we have some more relationship between these two threads. So, but maybe we want to start with this msync. So in the case of msync, right, we put an msync in here. Sorry, fence. Yeah, we'll just leave it like that. Things should slow down. Because now we're saying we're reading X, we're incrementing it, we're storing it, but then we're going to have to wait until the store has finished before we move on. Then again, maybe it's not so bad. Right? How long is this store going to take? If we start like this. So now they're on their own cache lines, right? The store should be 4 cycles, probably. So maybe it isn't such a big deal. On the other hand, we can't do any, well, maybe we can do some speculative execution. We can do the increment here. We can check the condition in parallel. Because we're not doing any memory accesses. mfence is only related to memory. Actually, max either is could be that it's reading that. Let me change that just to be safe. We'll make that a define. Since it was a const, it probably shouldn't go and read that from memory. But anyway, let's leave it like this. Okay, so I guess we would expect some slowdown, but the store buffer really isn't that much of a performance hog here. So let's see what happens. Okay, so we went from 300 milliseconds to about 1.7 seconds. And so what does that mean in terms of cycles? It's 100 million. See, so we're using about 20 cycles per iteration around this, right? And I think 100 million, we have 2.2 billion cycles. So for each one of those, yeah. So 22 cycles per iteration around with the mfence. And without the mfence, it was only third of that's 7 cycles around, about, right? So we were doing a load. It has to be a load because these are volatile. So we'll have a load, have an increment and a store, but then, and those are sort of dependent, right? You have the load, you can't do the store before you've done the load, you can't do the increment before, you can't do the store before you've done the increment, so they're all kind of adding up together. Whereas the rest of the loop, this part can run in parallel with the increment bit. So I guess 7 or 8 cycles, we can't really do any better than that, right? Because the load will be a few cycles, and there's an increment, and then there's a store. We're kind of limited by that sequential execution. Okay, so we ended up with what? Let's see, about 20. Yeah, seems like quite a high cost. Okay, let's try if we're just not running an mfence on one of them. So now the question is, is there any interference between one core having all these mfences and the other one? Any thoughts? There should be no interference, right? Because they are accessing different cache lines. Everything ought to be independent. In fact, we get about the same execution time. The user time is much less. Why is that?
The one with the fence is still the long pole in the tent.
Exactly. So we have a pthread join at the bottom. We're just waiting for everyone to finish. One of them is slow, the other one's fast. So that's okay. Okay. So what's going to happen then if we use the same cache line instead? Right, so I get rid of this alignment. So in this case, we have the two threads accessing the same cache line, right? But they're running on different cores, so something's different here. Now the store buffer, right, is waiting for the other core to finish and hand over the cache line. We have one cache line going back and forth. Without the M fence, it apparently wasn't so bad, right? We went from 300 milliseconds to 500 milliseconds. So, yeah.
Why is it the same cache line when it's each way? There are two different variables, or each 64 bits?
They're 64 bits.
Oh, yes.
Yeah.
64 bits.
Yeah, so they're 8 bytes long. We kind of got unlucky. They could be on different cache lines, or I suppose we got lucky in this case because the topic of the class. But yeah, it's mostly because they're sitting next to each other, and the compiler in this case couldn't be bothered to spread them out. Okay, so all right, so actually let's just run this first, and then. So the M fence made it kind of slow on independent cache lines.
Wow.
Using dependent cache lines didn't make it so bad if you don't have the M fence, right? But with the two together, it's really horrible. So now we went from, what was it, 500 milliseconds, but with the M fence, it's 9.8 seconds. So what's the difference there? Why do these two kind of combine in such a terrible way, I think? Or let me put it a different way. Why is it that we didn't get a big hit for these unaligned? If we remove the M fence, it wasn't so bad, right? And they're still accessing the same cache line. They're reading from the, yeah. That's really fast, considering that there's fault sharing involved. And actually, if you look at the results, if we were to print out X and Y, they're correct. Everything's fine. It's only if we were to X plus both. Actually, let me do that too. And anyone want to take a guess? Is this going to run faster, slower, or the same? All right, faster, slower, same. Okay, slower or the same? Yeah. Same. It's not correct anymore. Yeah, we're not even printing it out, but yeah, this is incorrect values now. The reason that it performs the same is that the CPU doesn't care. Right? We're talking about cache lines here. In terms of correctness, we do care. We're going to get incorrect results if we don't have the M fence. I think with an M fence, we should be OK. In fact, maybe let me just put a print statement. That doesn't hurt. What? OK. Right, OK, so that's nice and correct. And, well, we know it's going to stink with 2 X's, but let's just do that. Yep. So we didn't lose so much. I mean, that one's obviously going to be 0 because, well, we didn't increment Y anymore. But we lost a few of the X increments. Not so many, but yeah, pretty bad. And if we stick an M fence in there, actually, let's take a moment to think about that.
You lost a lot. Shouldn't it be 200 million, or is that a billion?
That looks like 99 million, right? And it's going up. I think we made that 100 million.
So shouldn't that be 200 million if everything was working properly?
Oh, yes. Very good. Yeah, of course. It's twice as many increments to the same variable. Absolutely right. So we lost more than half. Yeah, thank you. Yeah, that makes more sense, actually. Okay, so what did I do now? I put this m-fence in here. What do you think? What will we get then? We know it's going to be slow. Right? We already did that one. But how many increments are we going to get?
200 million.
I don't know about that. Closer to 200, yeah. Yes, I think it'll be closer. I haven't tried this experiment, but I'm thinking it'll probably be over 100 million, but yeah, we're going to lose some. So this actually allows us to read the x concurrently for both of them, right? And then plus plus. Now, if they are perfectly synchronized, they perfectly go together, then we would get 100 million, but probably one of them will start a little earlier. So we'll get a little over 100 million, I would think. It's hairy stuff. Oh yeah, that took a little while to run. Right, so we were wondering why is this, yeah, go ahead.
But in the previous experiment, why will we be worse than half?
Well, so you could imagine the first thread running up a few million, and then comes the second thread. It read an old zero. Like, oh, let's not do a few million. That's kind of unlikely. But okay, so one thread reads an old value. The other thread does a few increments and writes it. And then comes the first thread and writing back like an increment of the stale value. So if at any point there's two increments happening for one thread in between, then we would lose more than one. That's probably what happened. Okay, so what happened here? Right, so we saved a few more of them, but it's really not good. mFence didn't fix it for us. It's actually nice. It'll lead us to another important piece in this lecture. So, but first of all, I wanted to figure out why is it running fast? Well, it's like not so much slower when we have these unaligned variables sharing a cache line without the mFence, but with the mFence, that's where it really hits, like this false sharing. What's going on there? Yeah.
Is there a contention to get the same cache line exclusively?
Yeah, but there would be in both cases. Like we're trying to write to the same cache line. But the mFence somehow makes it much worse. How much worse, actually? So this was what 10 seconds? And it was a half a second before, so it's like 20 times worse. And it was only, let's see, just the mFence itself. It took about 2 seconds to run, right, with separate cache lines. And then with the mFence, let's see, and then there's the same cache lines, then it's 5 times worse. Right? Yeah. So the CPU is doing something here that allows us to make progress, even though we're sharing a cache line. Right? The two CPUs are sharing one cache line, and they're kind of making progress unless we have this mFence, and then it can't make any progress. What is it?
Because you're waiting on the store buffer to.
Yeah. So with this mFence, we can't make any progress until the store buffer is empty. But if we, so now imagine, so in the case where they have the separate cache lines, it's not so bad because it's only a 4-cycle wait, right, to actually finish that one. And maybe we can do some other sort of register work in between. It's not really a big deal. In the case of no M-fence, but a shared cache line, now they're contending for this shared cache line. It has to move back and forth, and it's really slow, except the store buffer kind of hides that. So you're doing all these, we're doing a read. It's fine. We're reading old stale cache value, let's say. Or maybe it's coming out of the store buffer by now. It's one of those read after writes things out of the store buffer. But anyway, we have a stale value locally. We'll use that. And then the inc, of course, that's fine. And then the store just gets appended to the store buffer. Right. And then we go around again. Do the read, inc, store. Over and over and over. Just fill up the store buffer. At some point, the buffer is full. Then we can't do anything. So now we really have to wait for the cache line to make it over, and then we can flush all the stores in one fell swoop and then go back. So essentially, we get to sort of amortize that cost. The cache line moving from one core to another core over all those entries in the store buffer. I think the size of the buffer is like 56 entries or something on this machine. We didn't get 56 times faster. We probably didn't even fill that store buffer. The cache line made it over long before that happened. But so, yeah, so the store buffer allows this parallelism, but at the cost of reading stale values. In this case, there were no stale values. Well, there are stale values in the case of the x on both sides. But if it's an x and a y, it's not, the values aren't stale. The cache line is stale, but the value we're interested in is still the correct value. Right. So anyway, the M-fence prevents us from having that parallelism. Yeah.
So if you know that this is causing such high delay, then why not eliminate duplicate entries from the source? Basically, you're writing into the same query. So somehow we can optimize it to just formulate the value to this one.
You could imagine that the CPU could do something like that. Right? It's a little tricky, because there's a guarantee that all of the stores are visible in the correct sequence. Right? The total store order is part of the memory consistency guarantee provided by Intel. So you could get a situation where if you take a shortcut like that, so you're saying, oh, we have a store and a store buffer to X way up here. Here comes another store and a store to X. Let's just overwrite that one. Like, make it happen immediately. So now all the other stores that were before kind of move up, get passed by. If you have a dependency?
If you are waiting on some intermittent store, another operation.
So the problem is you don't know what the other cores are doing, right? So that's why we have this consistency guarantee. Otherwise, you don't need to worry about it. But the total store order is all for multi-threaded execution. Okay, the M-fence didn't actually help in this case, all right? Sometimes it's a really useful instruction. I like it when you say something like this. Let's see. Oh yeah. So say you have something like this. While not ready, value equals shared variable. Right. So in this case, we're waiting for some other thread to set the flag to ready. And this is in order, right? Any store. So the other thread, it sets the shared variable first to the correct value, and then it sets ready to 1, and then we're good to go. And because of the total store order guarantee, it's fine, right? Except reads are allowed to go before, oh sorry, in this case it's actually fine. There's 2 reads. The reads can't go before other reads. In this case, it's fine. I need to work out a better example. on the x86, some things are nicely taken care of for you. And this one actually, yeah, I need a better example. And these things I can't make up on the fly. All right, let's try something else. So we talked about atomic instructions a little bit in the past. So we have two choices here. In order to make the classic ringtone. In order to make this example produce the correct value, we could acquire a lock around x, right? And then increment inside of the lock. I think we've done that in the past. I think we'll just skip it. We know that it's slow. Right? So there's an alternative, and that's called atomic instructions. In this case, we can use atomic instructions directly to execute this, because it's such a simple thing. There actually exists an atomic increment instruction in the x86 instruction set. So we can try using that directly. There's these, they're called compiler intrinsic functions that kind of wrap all these assembly things. They go something like something like that. I don't remember the intrinsics, but it's probably a little more than that. We can use these C functions to just generate the assembly straight in the code. There's no overhead to it. It's just inline and nice. But I would rather this time use inline assembly directly. It's a little more complicated, but it makes for a more fun experience. So let's do that. So we don't. This actually produces potentially produces two different sets of instructions. It might be a move and a add and another move, right, in and out of the registers, or it could be just an inc. So let's start by replacing it with the non-atomic version. Pretty easy like this, so we'll do that. That's it. All right. So this is interesting. It complains. It doesn't know what I mean. So usually the compiler or maybe the assembler tries to be nice to us, tries to infer what we meant. Inc is not actually an instruction. It's not an x86 instruction, but there are many x86 instructions that are almost like that. There's the inc B and the inc W and the inc L and the inc Q. It doesn't know which one I meant. If I'd provided a size, it would work, but we'll just, in this case, we'll just tell it. So if I'd provided a register name that has a size 64 bits, then it would be fine anyway. But in this case, we have to tell it what we meant. This here, who's familiar with this inline assembly, by the way? Oh, nobody. All right. Yeah, please complain more loudly when you. OK, so what's going on here? ASM just says we're going to provide a string of inline assembly. And then the rest of it that follows after are constraints on that string, on that assembly that will be produced. Volatile says this bit of assembly could be changing other variables, and it can't really be moved around. So you could potentially remove it. It might be OK to eliminate this code, but you can't move it up here. That's not OK. So you can say ASM, and then it could potentially get a little more unpredictable. We'll stick with volatile for now. OK. The first string is an assembly string that just it's just assembly code, basically, except for this part. This is one of the arguments provided later, argument 0, well, the first argument, right? And then after the colon comes a constraint saying, oh, the 0th argument is just in order here. is a memory operand. So in here, it will be replaced by an address, not a register. So increment the memory operand x. So it'll replace this. In assembly, it will just become inc x, right? Because x in the assembly will be sort of the address of x. And then you can specify a few other things. So plus here means we're not only using x, like not only reading x, we're also writing to x. So it'll change x as well. If I say equals, it says we're only writing to x. This bit of assembly doesn't care what the value x was in the past. That's useful for optimizations. Right? You could imagine that we're doing some other work with x here, overwriting it and putting some new value in x, and then comes this to just overwrite everything that we did. Now the compiler can eliminate all those other instructions above. So this is a sort of a constraint. But inc clearly both reads and writes. After this comes, now yeah, I'll just do an example here. So the next one, after the next colon, these are just inputs. You're not supposed to provide any, at least if I remember correctly. Here you don't get to provide any pluses or equals. You just say these are just read values. In this case, so I could say %1 here, and it'll be whatever is specified from here. What did they say here? Well, they said this is also x, right? But I want you to put the value of x in a register before running all this. So it'll be any register. It might be RAQ, let's say. So the compiler will first generate code that says move x into RAQ, and then here it'll just replace %1 with RAQ. So if you specify R, that means it's a register, M means memory, and you can also, there's lots of things you can do, but these are the most important. You could also say like A, and that means it's got to go in register A. Or I think you can say like R10, this one has to end up in R10. So before you start running this stuff, make sure you put the value in R10, value of X in R10. We could probably try this, see what it does. Let's see. Wow, that's a lot of junk. Aha. Maybe that's the problem. No? Why do we get so much crap here? So, oh, I see. It's the -G that's screwing with us. Probably. Ah, that's better. Okay. So that was all the debugging symbols kind of looking like assembly. All right, so let's see. So thread func B, I just thought we'd see what it generates. Play with that a little bit. Okay, so here it is. So this is the barrier stuff. And now we're moving X to RDX, and then we're doing this increment of X. So here's the address of X. Now this is RIP relative addressing. That's just one way to express the address of X. So let's say we try this without, let's see, can we get rid of some more junk? These are kind of dull too. Oh, it's okay. Okay, so let's run another one. How many? Oh, I can do a head on it. Does that give us what we want? Not quite. 30. we're still thread func A. We want thread func B is the one we're playing with, so I'll do a little more. Okay, here. Good. All right, so what are we doing? Yeah, here's our inc with the x replaced. So let me just try putting a %1 here instead. And now, I guess R10 didn't really do it, but let's see. Matching invalid operand number. Let's see. We do like this instead. Okay, so something wrong with R10. I don't remember how you get in a certain register. Now we told it we want it in a register. Let's see what it did here. Is this A? Okay. Somehow I lost the 50. Okay, so here it is. Right. So you see this generated code here? Right. This bit tells the compiler, well, you got to move the value of x into RDX first. And then now we've replaced the %1 with wherever the compiler decided to put it. Let's do one more. I'll just tell it, I think it's like that. Hopefully it'll end up in RAX. Yeah. All right. So there's the sort of the general idea. This is really useless code because we're incrementing something in a register, and we're saying that's just input. So we're going to lose all those increments. Like it's just sitting in RAX. No one's using it. You could imagine like this instead. Let's just see what happens. I'll get rid of this junk. So now we're saying, oh, yeah, we're incrementing x here, the plus. So that means it's going to be both a read and an assignment. So we're incrementing x, but I want it in register A. So this inc here will just do an inc RAX. But we've told the compiler you have to move the value into RAX first before running this, and then after you have to take the value out of A, RAX, and put it back in X. So now we should generate a little bit more code. So here we have the put it in RAX. Here's increment RAX, and there, move from RAX back into X. And why did it become RAX instead of RAQ? Oh, sorry, it's not called RAQ, isn't it? It's RAX. Yeah, I'm thinking EAX. I got the register names confused. Okay, RAX is the 64-bit version. There's no RAQ. It's the instructions that end with a Q, not the register names. Sorry. Okay, so good. There's our increment. Now we kind of have an idea of what this thing is doing, I think. So, and then, okay, so these were input operands, input-output operands, just input operands, and then clobber in the end. So here we might say, let's get a little nasty. We might say, oh, we actually overwrite RSP in here. That's not a good idea. You don't want your assembly to be overwriting RSP. And we're not actually doing it. We're just telling the compiler, like, watch out, because I'm going to overwrite RSP. So if you like your value that you have in RSP, keep it somewhere else. Let's see what it does. Oh. No, that's not the one. I guess it doesn't like its RSP. What? Why is it not upset by that?
Is it because you specified RAX?
Now this is a clobber. It says, like, I am going to overwrite RSP for you. And it's not restoring RSP. That's confusing. Let's try another one. Okay.
Oh, it's a leave instead of a ret.
Oh. But no, that's okay. A leave is just it's something followed by a ret. It's like a restore the RBP thing, and then, yeah, it's restore RBP and then ret, I think. That's not it. Maybe I somehow specified this wrong. Anyway, let's try another one. We also have our here in EDX. That's the I that's iterating around. So we can overwrite EDX instead. Maybe there's something special about RSP. It's a really dumb idea to be overwriting RSP in your assemblies. Maybe there was a warning here that we missed. No. Beats me. But maybe I'll experiment with that on my own time, and I'll let you know what happens. But let's try overwriting EDX. And see what it does. So now the compiler ought to put this I in a different register. Right? So now it's an ECX, because it knows EDX isn't safe. And if you clobber too many things, you can keep doing that. Let's do a few more. Where has it got it now?
EAX.
Is it an EAX? Oh.
You did not specify that.
Oh, wait, is this the 30? No, this is the 50. Oh, but we're still in A. Yeah, maybe it got a little longer. Is that it? This is thread func A. We want B. Did it move it?
An error.
Oh, that's why. Okay. Unknown name. What is it then? Is it? I could have sworn it's with a comma. No, it's not with a comma. Is it with a space? Maybe. Crap. Maybe it goes like this. I should have tried this ahead of time. Yeah, okay, so that's it. All right, now we're going not too far. Func B. Is this thread func B? Oh, this B, yeah. Right, so now it's in ESI. Okay. Yeah, there's so many registers, like there's 15 of them. Let's not do it. But you could keep specifying them here. And at some point, you put everything, except maybe ESP. There's going to be something special about ESP. Then the compiler will have to start saving its values onto the stack before making, even using RAX. Right? But anyway, the compiler will make sure that things don't get overwritten or lost as long as you tell it what you're up to inside of this assembly. But it doesn't know what you're doing inside the assembly. Okay, actually, let's try one more thing. I want to drop this. Okay, so this is what we would expect. This is proper memory thing. But I've got an X++ here, and I want it to go like that. Oh, that's not actually possible. Oh, actually, it doesn't matter. Probably doesn't matter. Let's see. Right. Okay. So there we go. It's with func B. Huh. I expected the compiler to pull out this add, but it's still there. See this add? I thought that would be gone because it's useless code. We're just assigning, but maybe it does have some idea of what we're doing in here. Huh. Anyway, let's move on. So what I wanted to try is this atomic increment. These are just increments. They're the. Why didn't it complain about this one? Huh. The normal increments, they do the same thing as just a move and an inc and an add and a store. So you would be losing part of your excess. Let's get back to compiling this properly. There. See how long it takes? Okay, so it's actually the same. So I think in this case we still, yeah, they're on the same cache line. So it's, you see, it's the same performance as our previous code that was a move and an add and a store. That's because the inc actually expands into those three microcode instructions. Okay, so we see we get the wrong values here. If we want it to be the right values, you can just say lock. So these are the atomic instructions, or I think in the Intel developer manual they're called locked instructions. So the deal with locked instructions is there is a total order across all the CPUs of all locked instructions. And this actually expands to several microcode instructions, but that doesn't matter. The whole thing executes atomically. So now the read, the inc, and the write in here happen together, and then that one gets to go. So that means we should get correct performance, correct output. But what kind of performance can we expect? This is kind of a tricky one, I think. So there's a couple of choices. Well, I guess what really should happen is the cache line should go from one side to the other side and then back and forth like this, right? Keep incrementing. And so that's going to be slow. There's relatively long latency to move the cache line. So maybe it ought to be similar to the mFence case.
What latency should we generally expect moving?
So it depends on the distance between the cores, but within one socket, you could expect, let's see, so that's like an L1 miss, or maybe call it an L1 and L2 miss, but it'll hit at the L3, so it'll probably be something like 40 cycles. But then if it's on a different socket, then a couple hundred cycles. But it's the same as with the msync, at least. So let's see. Yeah, kind of sucks. It's actually kind of interesting, I think. It's not obvious that it has to be slow. There it is. Even slower than the msync thing. Of course, the msync thing didn't produce the correct result. So there's that.
Is it because there are more instructions to execute like in total order? Because mFence just provides guarantees that the writes will, that there are no stale reads to be done.
Yeah, so it's clearly harder to do an atomic instruction than an mFence. I think it took about twice as long, probably because we actually did twice the amount of work. We actually got twice the number of pluses done too. But it's not obvious that it has to be like this, because another correct execution would be to run all of these first, and then all of those. But there's a total order in the sense that another observer, no matter how many other observers you have, all of the increments happen in the same order for everyone. But it doesn't say that they have to interleave like perfectly like this. There's nothing like that. Actually, why don't we try see what happens if they go one after another. Okay, so it's the fact that the cache line is going back and forth that's making it slow. It's not the lock itself. We can try this a different way. So just use, at least we're using the same variable, doesn't matter. Same cache line is what matters. They're still on the same cache line, but we can change that. Keep them on different cache lines. So now it's essentially independent atomic instructions working on different cache lines, and there's nothing going back and forth. And then we're pretty good. So, okay. About a second. So the atomic instructions, they have to have this total order, even though they're operating on different cache lines. They sort of have to coordinate a little bit. I think that's what's making these things, well, that's one thing that's making atomic instructions slower than non-atomic ones, right? Let's just get rid of the lock. What do we get now? Does anyone remember? Oh, sorry. 300 milliseconds. Yeah, I think that's right. All right. So that coordination, well, there's a couple things going on with the lock, right? One is that they have to have a total order. I think that can't be cheap. And the other one is you don't get to reorder instructions. You can't reorder around this. So you can't go and continue on the next one here. Well, that's probably not it. Ah, yeah, so
You gotta get
probably this one has to leave the store buffer before you can start the next one. I would imagine that's what's holding us back. So, did you have another?
I think that I was trying to remark the same thing is that it won't let you read it now until the store buffer is cleared, right?
Yeah, probably. It's not completely obvious to me that it has to be like that. Because without the lock, it is allowed. So
But without the lock, you didn't get the proper result, right?
well, we do, because now we're working on different.
Oh, because you're working, yeah, but
Right.
on the same variable.
On the same variable, you don't. No, that's right. But no, actually, so here they're on different cache lines even. So I don't really see how the two interfere, even if they're. Yeah, so with different variables, different cache lines, they don't really need to communicate, these two.
But you couldn't do a speculative read on a locked write, right?
Right, but that is finished.
Mm-hmm.
So that's the question. So the ink, the lock ink, expands into this read increment write, and then we've already finished the write. Well, it hasn't made it out to main memory yet. But this one local chip, it's not obvious to me why it can't now read from the store buffer again.
Yeah, I see that.
It could be that that's for sort of fairness reasons. So what we saw there was that both chips get to access the variable at the same time. That's why it's going so slow. Right? You could imagine that, oh, as long as you keep accessing this variable, no one else gets to touch it. And then it's going to run a lot faster. And that'd be great. Of course, the other threads might not like it because they are completely blocked. They don't get to access the variable. They're stopped. So maybe it's some sort of balancing performance versus fairness that's going on there. I'm not sure. Anyway, it would seem in this case that increment and then an M fence draining the store buffer has the same effect as a locking. We get the same result, and if it is the fact that you can't continue to start the next iteration until you drain the store buffer with the lock, then maybe an M fence would do the same thing. It took 1 second with the atomics. A little more. Yeah. So I think if we diagnose this a little further, we might find out that the lock-in actually allows several ones to run on one core before going over to the other core. We've seen this in some of my research. Like if we just store the values locally to see like, oh yeah, I did increment number 15 and 16 and 17. See that sometimes you get a whole string of increments back to back on one core, even though multiple cores are trying to access it. So it could be that that's why the lock-in is running faster than this inc fence. I'm not sure. Okay. I think we'll leave it at that for sort of the cache coherency communication discussion for now. Any more questions before I show a couple of little compiler tricks? Right. All right, so most of this stuff you wouldn't really use, right? It's not that on a normal program, you often run into these problems. Usually your program doesn't look like this. It's weird programs. Right? So the whole point of studying it is to understand the machine so that when the weird thing does occur, you know what to look for. But we very commonly use an optimizing compiler. And optimizing compiler can only do well if we actually tell it what we mean. And there's some ways, sometimes we have to be a little more explicit than we usually are. So I had a few examples. Let's see if I have a compiler fence. Let's see what's in this. Oh. Oh no. Okay, good. Right, so time for some simple code again. So we're not going to try to look at performance anymore. Now I just want to see what kind of assembly is generated. And there's I really like this way. As someone showed this compiler explorer. There's a whole bunch of different websites for it. That's cool too. I like the command line. If you just say like this, right, it generates the assembly on the command line for it. And this is such a small program that we can very easily read it. All right, so we ran into this before. Here, we haven't said anything about the C being potentially accessed by other threads. And so the compiler decides to just stick here. It puts, I think, probably loads C at some point, yeah. Loads C and then increments C by 100, by a million, instead of going around a million times, and then writes it back to C. So that's fine. One way that we could address this is to say, oh, C is volatile. But that could be a little extreme. Like, it says that, oh, all the time when you access C, someone else might be accessing it. So you have to load, every access to C has to be an actual access. It can't just be stored in a register. But we could say it's really only sensitive in here, in this loop. Elsewhere it's fine. So if we want to just make the compiler not pull this weird trick inside of this loop, we have to tell the compiler, well, C could change here. So how would we do that? Now we get back to this assembly thing. Actually, we don't need any assembly code. We just put memory in the clobber list. There we're saying, oh, all of memory could change inside of this loop. So it's not actually safe to just skip all of these iterations, because you will not get the same result. So here we're doing this cheat increment, and now we're actually adding to C over and over. All right, nice. This is not a load and an increment and a store. This is actually adding directly to a memory operand. I didn't know you can write that. x86 assembly. OK. Everything runs the same speed anyway. OK, I like that one. Yeah.
I had a professor yesterday mention that if you do ++C, it actually does an increment versus C++, but I don't know if that's actually true.
I would imagine that's up to the compiler a little bit. Why don't we try it? Looks the same in this case, yeah. But probably if we use C for anything else inside the loop, it might generate different code because one of them would leave value in a register. If you do the move and an increment, now it's in the register for use, whereas this one doesn't leave it in a usable state. All right, that's one. Let's see. I had some notes here with a couple of things I needed to do. Oh yeah. And then if we have little functions, functions have some interesting aspects to it. So let's try this. Start with. Just do the work in here instead. OK, so it's doing the same thing, right? We're just saying, call this function to increment C. So this is an optimizing compiler, and everything is visible while we're compiling this file. This is actually a very important point here. Compiler always, sometimes you would say on the command line, you would say, oh, this C file, that C file, this C file, right? What it expands to is go and compile that C file independently to make a .o, compile that other C file independently to make another .o, and then link them together. So at the compilation and optimization stage, you only have one C file at a time. So let's see what happens here. We have our function f, and it does what we would expect. Right, so this is indirect. RDI has the pointer in it, so it just says increment whatever the pointer is pointing at. But look at this. There's no call. There's a call to printf, but that's a different story. Right, because the compiler knows what's inside of f, so it might as well just do it in here. It's a lot of bother putting stuff in registers and making calls. It goes pretty slow. So it just takes that statement, the ++, and puts it in here. But then it sees, oh, actually, I don't need to do it at all. I might as well just get rid of the loop. So we're back to the original statement of just add 100,000 to the loop. But imagine you have it in a different object file. What's going to happen now? No, we're just compiling here. We're not linking. It has no idea what's inside of f. Right? F isn't even declared yet. We're just making a .o here. So there's no hope. For little things like this, if you wanted the compiler to inline, then you can put the f inside of an include file. Include files are processed by the preprocessor, right? So whatever the C compiler does, it just copy pastes the content of this into this file, and then runs the compiler. So now you have your function inside of your C file, and that would work. But if you link something in, it won't be quite the same. All right, but what if, oh, drat, we're out of time. So next time we'll take a look at what happens inside of F. There's a lot we can do. If we have this in a if we have our function f in a different object file, there's ways that we can declare f that makes it slow or fast. It's also compiler optimizations. Okay, so good luck with the. Actually, did you all turn in the homework already? Was it due now? No, it's next week. Yeah, okay, good. Sorry. Good luck with the homework then.
What kind of, like, are we limited to the changes that we might make